What's happening, everyone? In this video we'll be learning about the AVL tree, which is a slight modification of the binary search tree that provides more efficient lookup, insertion, and deletion operations. At the beginning of this lesson we'll cover some background on the AVL tree, then towards the middle we'll open up our coding editor and actually implement an AVL tree using the Python coding language. The final code for this lesson, as well as the code we build off of, will be linked down in the description. As always, if you enjoyed this video, consider throwing me a thumbs up, drop a comment if you have any questions, and be sure to subscribe to stay up to date on my Python programming content. Before we actually start talking about AVL trees, if you don't have much experience with traditional binary search trees, I would recommend starting off with our prior video, the link to which will be in the description. We'll also be building our code in this video off the code we developed there, but as I said before, the code we start with will also be linked in the description. So to start off with some history, the AVL tree was developed by Georgy Adelson-Velsky and Yevgeny Landis in 1962. The pair published their new binary search tree scheme in a paper named An Algorithm for the Organization of Information. This publication was on the heels of the original design of the binary search tree, which had only just been officially invented in 1960, 2 years prior. The innovation of the AVL tree, and what separates it from the ordinary binary search tree, is that it specifies a built-in balancing operation. This balancing operation takes place after insertion and deletion operations that cause the tree to become unbalanced. So on this slide we have some examples of binary search trees with different amounts of balance. Just by looking at a picture of a binary search tree, we can tell whether or not it would be possible for it to be an AVL tree based on how balanced it is. We'll get into the specifics later, but for now we're just going to go through some examples and get a better idea of what an AVL tree looks like. The leftmost picture is a perfectly balanced tree, also called a full tree, where all possible locations are filled down to the bottom, and of course, being that this is perfectly balanced, this would be a valid AVL tree. In this case, insertion, deletion, and lookup would run in big O of log n time, where n is the number of nodes in the tree. Take note that with all binary search trees, insertion, deletion, and lookup run in big O of h time, where h is the height of the tree, but in the case of a fully balanced tree, the height of the tree is actually log n, so that's where that definition came from. In the middle picture we have a fairly balanced tree, and this would actually also be a valid AVL tree, as there is some built-in lenience in the design of the self-balancing feature. On the right side we have what looks like a linked list, but is actually just a very unbalanced binary search tree. This is exactly the situation the AVL tree design is trying to avoid, because in this case insertion, deletion, and lookup would all degrade from logarithmic to linear complexity, which is a massive slowdown. Again, this simply comes from the fact that our algorithmic efficiency for the BST is big O of h, and in this case h actually equals n. Now that we have a rough understanding of balance visually in binary trees, we can nail down the specifics. According to the AVL rules, for a node to be balanced, the absolute difference between the heights of its children must be less than or equal to 1. And if a child is missing, it's treated as having a height of 0. For a tree to be balanced, this rule must hold for every single node in the tree. The way we actually define height here is also important. The height of a node is defined as the maximum distance from that node to a leaf node. Defined recursively, this means the height of a node is 1 plus the maximum of the heights of its children. The recursive equation, as you can see on the slide, will pop up several times once you actually get down to coding, as it's the main tool we use to set the height values in the tree. Now on the bottom of the slide we can see some examples of binary search trees where the height of each node is labeled in blue, so we can get a better idea of what these rules actually look like in practice. On the far left we have a simple case of a root node with a single child. To compute the height of the 15 node, we can use a recursive equation and the fact that this node has no children to get a value of 1. Again, using the equation, the height of the root node is simply 1 plus the height of its child, or 2. Now to check if this tree follows the AVL balance rules, we can iteratively check each node. Starting with a root node, its left child has a height of 0, and its right child has a height of 1, meaning this node is balanced because the height difference between its children is not greater than 1. Now looking at the 15 node, both its children have heights of 0, meaning of course it's also balanced. Because both of the two nodes in this tree are balanced, we can confidently say this tree is balanced according to the AVL rules. In the second example, we've added on a left child to the root, but of course again the root holds the same height value because the height of its left child is again 1. This tree is also balanced according to the AVL rules. In the third example, we've added a right child to the 15 node with a value of 20. Here we can see the height of the 15 node has been incremented to 2, and the height of the root has been incremented to 3. If we perform our balance analysis on each node, we'll again see this tree is balanced because there exist no nodes whose children have height values differing by more than 1. Looking at our fourth and final example, we can see we've removed the left child from the root while keeping the rest of the tree intact. This tree is now unbalanced because the root node has a left child height of 0 and a right child height of 2, and this height difference of 2 is larger than that allowed by the AVL rules. Now that we can distinguish visually between balanced and unbalanced binary trees, and we understand the equation used to evaluate whether or not a node is balanced, we can move into how we actually rebalance the tree to fix these problems. So if we wish to rebalance the tree, we're going to need some operations that enable us to rearrange the nodes without violating the sorted order of the values of the nodes themselves. Because recall, obviously, when you have a node, all the children to the left have to have a value smaller and all the children to the right have to have a value larger. We'll first talk about the operations, then discuss the situations in which we'll make use of them. So at this point, all you really need to understand is the operation itself, not where the nodes actually come from. So the first of the two operations in our toolbox is the left rotation, as you can see in the picture on the slide. On the left of the picture, assuming that T1 through T4 nodes are all at the same height, our Z node will be unbalanced because the height of its left child will be 2 less than the height of its right child. To fix this, we'll perform a left rotation on our Z node. In the left rotation, we take the middle value node, in this case Y, and move it up to the top of the subtree. In code, this would mean changing the parent of Z to point to Y rather than to point to Z. We then hook up the smallest valued node, Z, to the left child of Y, and preserve the largest valued node, X, as the right child of Y. We preserve all the children of X, but move the original left child of Y, T2, over to become the new right child of Z. The left child of Z, T1, remains in its original position. To check to see if this operation respects the BST rules, we can inspect what is being stated by the tree structure before and after the operation and ensure it's the same. So on the left, before the rotation, we can see X is greater than Y because it's the right child, and Y is greater than Z for the same reason. On the right, again, we see X is greater than Y, and Z is less than Y, or alternatively, Y is greater than Z. So interestingly, assuming the BST was structured properly on the left, it will remain so on the right, and we won't invalidate any of the relationships among the nodes by performing this left rotation operation. The point of the left rotation, as we discussed earlier, was to balance the node Z, and as we assumed in the beginning that T1 through T4 were all at the same height, our node Z is now balanced because both its left and right children, T1 and T2, are at the same height. At the same time, nodes Y and X remain balanced, so our left rotation has successfully fixed the situation. The second operation we can harness to rebalance the tree, while at the same time preserving the ordering of the nodes, is the right rotation. You should notice pretty quickly that this is very similar to the left rotation, only it's basically flipped horizontally. In the right rotation, we again take the middle valued node, Y, to be the new parent of the subtree. We then preserve X as the left child of Y, and hook up Z as the new right child of Y. The children of X remain the same, and the old right child of Y, T3, is hooked up as the new left child of Z. Again, assuming T1 through T4 are all at the same height, this operation will fix the initially unbalanced state without violating any of the node relationships, similar to the left rotation. So now that we understand, or at least have seen, the two operations we can use to rebalance the tree, we'll take a look at when we should actually use them. The first scenario where we may need to perform rebalancing is after an insertion into the tree. The second is deletion, but first we'll take a look at insertion. The insertion operation for an AVL tree begins with a standard binary search tree insertion. After that, we then traverse up the tree, starting with the parent of the node we just inserted, and continue traversing up until we reach a node that's unbalanced, or the parent of the root node, at which point we know we're done. During the traversal, we maintain a list of the nodes we've looked at, and each time we inspect another node, we place it at the front of this list. And this will make more sense once you actually see the code. If we did find an unbalanced node during our traversal, remember an unbalanced node is one where the heights of its left and right children differ by more than 1. There are 4 possible configurations it can be in with respect to the prior 2 nodes we just looked at during the traversal. You can see basic images of the 4 configurations at the bottom of the slide. Here we let Z be the unbalanced node we just found, Y be the child of Z we traversed over previously, and X be the child of Y we again traversed over previously. This is the reason we maintain the list of nodes we've traversed over, so if we find an unbalanced node, we can easily remember where we came from to get to it. As you may have guessed, for each one of these 4 configurations, we have a slightly different way of fixing the imbalance, but they all involve 1 or 2 rotation operations. The first configuration we'll call the left-left case because Y is the left child of Z, and X is the left child of Y. To rebalance this situation, all we need to do is perform a single right rotation on the Z node. In the second configuration, the left-right case, we'll need to perform 2 consecutive rotations. First, a left rotation on the Y node. Note this doesn't affect the Z node, and then a right rotation of the Z node. In the third configuration, the right-right case, all we need to do is a single left rotation of the Z node. In the fourth and final configuration, we'll again need two rotations to fix the imbalance. First a right rotation on the Y node, then a left rotation of the parent Z node. On this slide we can just see a summary of all the four configurations our nodes can be in if we find an imbalance after an insertion. They're actually pretty easy to remember. In the cases where we need two rotations, the rotations are just the same as the name of the case. And when we need a single rotation, it's just the opposite of the name of the case. Obviously there isn't really a need to memorize this unless you have an exam on the topic, because it's all just going to be hard-coded into our Python program later. The one last thing we need to cover before we get to coding is the second situation where we might need to perform some rebalancing, the deletion operation. It's not on the slide, but we begin the deletion operation similar to as with insertion, with the standard binary search tree deletion method. Then the way we handle the rebalancing is almost a mirror of how we handle the insertion rebalancing, but with two major changes. The first is that, in the insertion case, once we perform a single rebalancing, we can be sure that the rest of the tree, or more accurately all the nodes above the current node, are also now balanced. This stems from the fact that when we perform an insertion, we're incrementing the height difference in the affected nodes, those above the insertion location, by at most 1. Then if we find an imbalance, our rebalancing operation will decrement the height difference in all the affected nodes by at most 1. So in effect, we'll never have a situation where there remain imbalanced nodes in the tree after a sequential insertion and rebalancing, because both operations are working in different directions and canceling each other out higher up in the tree. This doesn't hold true in the case of deletion, because when we delete a node, we're possibly decrementing the heights of the nodes higher up in the tree. Then we find an imbalance and perform rebalancing, we're again decrementing the height of the higher up nodes. Because of this, in the case of deletion, we need to continue traversing up the tree, performing rebalancing operations when we find imbalances, all the way until we reach the root node, whereas with insertion we knew we were done after a single rebalancing. The second major difference between rebalancing and the insertion and deletion operations is the way we assign the Y and X nodes. The Z node remains the same, it's just the unbalanced node we found while traversing up the tree. But rather than setting the Y node to be the last node we traversed over, we instead set Y to be the child of Z with the larger height. Similarly, we set X to be the child of Y with a larger height. This is in some ways easier than what we had to do for insertion, because we don't need to maintain a list of all the nodes we've traversed over. We can just calculate Y and X on the fly after we found Z. Besides these two changes, everything else between insertion and deletion remains essentially the same. Once we've found an imbalance, it can fit into one of the four configurations, and for each configuration we approach it with the same set of rotations. We've now covered everything we need to start coding, so we'll switch over to our coding editor and actually start developing the logic for the AVL tree. So as explained in the beginning, we'll be starting off with our code we developed for the standard BST. I've made a couple minor changes since the posting of the original BST video, so if you're coming straight from that, just make sure you pull the most recent copy from the GitHub. Now before we start adding the AVL code, we're going to switch to terminal real quick and make sure our original code actually works as we would expect. We'll just insert some elements, then print the in-order traversal. Since our in-order traversal came out in sorted order, we can be sure our BST is actually working properly. So the first change we're going to be making is adding an integer height attribute to our node class. Once a node is actually inserted into the tree, this value will accurately reflect the height of that node in the tree. Since we always insert a node at a leaf location, and the height of a leaf node is 1, it makes sense to set this value to 1 by default. The next change is we're going to simply change the name of the class to AVL tree to obviously reflect the fact that this will no longer be a regular binary search tree. I'm now going to be pasting in some code for a special function called repr, which is short for representation. If you haven't seen this sort of function before, if you declare a repr function inside of a class and you print an instance of that class, so just calling print and then the name of the instance, under the hood the repr function will be called to create the string that's used to represent the instance. So for example, if you had a student class and wanted the student's name to be printed when you print an instance of the class, you would just declare a repr function that returned the name variable inside the class. In the case of our AVL tree, it's definitely helpful to actually be able to see what the tree looks like. So in effect, that's what this function will do. I'd recommend just copying this portion of the code directly from the GitHub because it's pretty long and doesn't really have anything to do with AVL trees. We'll now be declaring all the functions we'll be adding to enable the rebalancing feature, as well as some helper functions. We'll explain the actual logic behind these functions in a bit. So now before we add the code for the new functions, we'll finish making our changes to the existing BST functions. First we'll be adding 2 calls to inspect insertion from within our original insert method. After we successfully insert a node, we'll pass the new node to our inspect insertion function so it can begin traversing up the tree to check if we need to perform any rebalancing. Next we'll alter print tree so when it's called, it'll print out the height of the node as well as its value. Now, similar to how we changed insert, we'll be making some changes to delete node to accommodate the rebalancing operation. If the node be deleted had a parent, we'll first update its height using the equation we explained at the beginning of the lesson, then pass it to the inspect deletion method. Similar to inspect insertion, inspect deletion will traverse up the tree, rebalancing any nodes it finds to be unbalanced. If you recall in the BST deletion function, we entered into one of 3 separate cases, where the third case was actually recursive. Because we definitely don't want to accidentally call our inspect deletion method more than once, we'll now be adding in a return after the recursive call in case 3. That concludes all the changes we need to make to the BST code, so now we can focus on our new AVL methods. The first one we'll complete is the inspect insertion function, which is of course called by insert after we've inserted a new node into the tree. The function has passed a single node, as well as a list called path that contains all the nodes we've already traversed over. Being that this is a recursive function, it's definitely a good idea to include a base case. In this scenario, since we traverse up the tree when checking for imbalances, our base case will be when the parent of cur node doesn't exist, or equivalently when we hit the root node. After checking the base case, we'll prepend the cur node to the front of the list of nodes we've traversed over. We'll then create variables to hold the heights of the left and right children of the parent of cur node, and understand one of these will be the height of cur node, but which it actually is doesn't really matter. After fetching the heights, we'll compare their difference to check if the parent of cur node is balanced. If the difference is greater than 1, we know it is imbalanced, so we'll have to perform some rebalancing using our rebalance node function. If you recall from earlier, once we found an imbalance after insertion, we need to get a handle on 3 different nodes. The first, we call Z, is the node that's actually imbalanced. In our function, this is the parent of cur node. The second and third nodes, Y and X, are the nodes we've traversed over previously that got us to Z, in this case cur node and the prior element on the path list. To simplify our call to a rebalance node, we'll first prepend the parent of cur node to the front of the path list. That way we can call the function, passing the first, second, and third elements of the path list as the only parameters. Again, these elements correspond to Z, Y, and X respectively. After calling rebalance node, we'll call return to exit the function. This is because, as we explained earlier, after an insertion we only need to perform a single rebalancing to know the rest of the tree will be balanced. If our parent of cur node was balanced, so if we didn't enter into the if statement, we'll calculate a new height for the parent equivalent to 1 plus the height of the cur node. If this new height is greater than the current height of the parent, we'll update it accordingly. This is the main way by which we actually update height values in the tree and propagate changes in height up the tree after an insertion. After possibly updating the height, we'll recursively call the inspect insertion function, this time passing the parent of cur node as the new cur node, and passing the updated path as the new path variable. Next we'll be covering the inspect deletion function, another recursive method. This method is called by delete node and is passed the parent of the node we've just deleted as the cur node. The base case for inspect deletion is similar to inspect insertion, except in this case we'll check to see if the cur node itself is known. This is because in inspect insertion we were checking the parent for imbalance, whereas with this function we'll be checking cur node directly. After passing the base case, we'll create variables to hold the heights of the left and right children of cur node, then check the difference of those to see if cur node is balanced. In the case that cur node is unbalanced, similar to inspect insertion, we'll need to identify our Z, Y, and X nodes. Z is simply cur node, and note, we're not actually creating a separate variable named Z, we'll just treat cur node as Z. Y is the child of Z with the larger height, and X is the child of Y with the larger height. Once we've identified our nodes, we'll call the rebalance node function, passing cur node as Z, and Y and X as, of course, Y and X. Remember, in the case of deletion, a single rebalancing may not suffice to fix the whole tree, so at the end of the function we'll call inspect deletion recursively, now passing the parent of cur node as the new cur node parameter. The next function we'll be implementing will be rebalance node. This is where we'll actually break down the execution into one of the 4 cases we covered earlier, and remember each case has its own set of rotation operations required to fix the imbalance. The first possible case is the left-left case, where y is the left child of z and x is the left child of y. In this situation, all that's required is a single right rotation of the z node. I'm not going to cover the rest of the cases in depth because we already went over them earlier, and they're fairly straightforward. At the end of the function, if we somehow didn't enter into one of the four cases, we'll throw an exception, as this would indicate a problem with the structure of our tree, and continuing on would possibly result in lost data. Next we'll be completing the right rotate function. As its name implies, this function will perform a right rotation operation on the input node z, following the methodology we looked at earlier in the video. The code inside this function is basically a direct Python analog of the transformation in the picture you can see on the screen. Take note that at the bottom of the function, we're also updating the heights of the z and y nodes using our 1 plus max of children equation. We don't actually need to update the height of x because its children remain the same throughout the transformation, so its height could never change. The next function to complete is left rotate. Again, this is simply going to be enacting what we see in the picture, so we won't cover it in much depth. At the end, we're again updating the heights of z and y, but leaving x the same because its children aren't changed. The last two functions, getHeight and TallerChild, are fairly simple and are used mainly as helpers by the functions we've already implemented. Notice that these are the only two of the new functions where we've omitted the underscore before the name. If you haven't seen our prior videos and don't have too much experience with Python, an underscore before a function name in a class is meant to symbolize that that function is private. This isn't actually enforced by the Python interpreter, so it's more of just a warning to other users not to call that function outside of a class. The reason getHeight and TallerChild are not private is that they won't actually be changing anything about the class, so it's safe to call them from outside without worrying about causing any problems. Inside getHeight, we'll check to see if the node we've been passed is none, which would only be the case if we were passed a child of the leaf node. If this is the case, we'll return 0 because back in the beginning we defined uninitialized children as having a height of 0. If we didn't satisfy the if statement, we'll assume the cur node is an instance of the node class and return its height. Inside TallerChild, we'll fetch the heights of the left and right children of the node we've been passed. We'll then simply return the taller of the two. That actually concludes the code for the AVL tree, so we'll now just write some simple code to insert a few elements and delete them, printing the tree after every step so we can see the rebalancing in action. We'll now switch to terminal and run the script. Although the print operation isn't perfect, you should be able to get a good idea of how the tree is restructured after we insert or delete elements that cause the tree to become unbalanced. I encourage you to mess around with inserting and deleting elements in the tree so you can see in real time how the tree fixes itself automatically, because it's actually pretty neat. That takes us to the end of this video, everyone. I apologize for how long it took me to finally complete this video, but I've been real busy lately, so I just haven't had much time to create all the resources I need to make one of these lessons. That being said, I'm definitely interested if any of you have suggestions for topics to cover in future videos. Although I do already have a bunch of stuff in the queue, I think the next topic might be hash maps. I'm also looking into some interesting projects to cover. Recently I was thinking about doing a video on recreating Snake the game using PyQt, and then doing a second video on training a neural network to win the game. In any case, I hope you enjoyed the video, and I'll see you guys next time.